Good evening, everyone. Today we are going to learn about some colligative properties. What we have started in the last class. Today, actually, we want to learn the colligative properties. In last class, we didn't learn the colligative properties. That means the property of solution which do not depend on the material, just depend on the quantity or number of molecules or concentration in case we can say. So the properties of solution which depend on the number of molecules or number of particles inside, not only not on any chemical entity. What types of chemicals present in the solution, it doesn't matter. So first I would like to learn something about the heat of solution. Actually, this is very simple. That means heat of solution. You are familiar with the word heat of combustion. Have you learned? That means, or heat of neutralization. Heat of neutralization, have you heard?
Yes.
That means when 1 mole water is formed from the reaction of acid and alkali, the amount of heat released when 1 mole water is formed from the reaction of acid and alkali. Just like if I write down like this way. There are so many markers, but not really. So many. Yeah, it should be. Then this compounds so just the reaction between any acid, HCl plus NaOH, what you get? HCl plus salt and H2O. Okay. All of you are very familiar with the chemistry. So just reaction between acid and alkali is giving salt, water, and some heat. So if you write down any acid, mostly any acid, but if I give you exact information, any strong acid and a strong alkali, then you will get the energy when 1 mole of water is formed. That means here we are getting the 1 mole of water. But if you have sulfuric acid, H2SO4 plus NaOH, in that case you can get 2 moles of water. Just if you balance it, because you need 2, and in that case you will need 2 sodium sulfate. You don't need to have, okay, because there is already. So just that, so you will get this, and then Na2SO4 plus 2 H2O, and then you will get some delta S. Okay. So the amount of heat released when 1 mole of water is formed by the reaction of acid and alkali, that is known as heat of neutralization. So we will consider that 1 mole of water is forming by the reaction of, it can be 1 mole of water, acid or alkali, it doesn't matter. Here we are getting 2 moles of water. That means how much heat or energy is released in this reaction? That will be heat of neutralization multiplied by 2, because we are getting 2 moles of water. So I have mentioned the definition like this way. When 1 mole of water is formed from the reaction of acid and alkali, that is the heat of neutralization. How much heat is released? Okay. Now, if we want to learn the heat of solution, here I have mentioned 1 mole water, therefore heat of neutralization. But if we say if you want to dissolve 1 mole of substance in any solvent, that means sufficient solvent, then some heat will be released or some heat will be evolved. So what is the heat change when 1 mole of substance or 1 mole of solute is dissolved into sufficient solvent? That is known as heat of solution. So if you want to make solution of sodium chloride, you have 500 ml water, is it? Okay, 500 milliliter of H2O, and then you are adding some salt. So if you want, you can dissolve. How much is the molar mass of sodium chloride? Molecular weight of sodium chloride? 58.5. 58.5 grams. So if you can dissolve 58.5 grams of NaCl into 500 ml of water, then it should be completely dissolved, no residue. Okay. So if you have a solution that you have dissolved 1 mole of substance, dissolving 1 mole of sodium chloride in sufficient solvent, then it will release or it will absorb some heat. That means the amount of heat released when 1 mole of any substance is dissolved into a solvent, sufficient solvent, it can take 500 or 100,000 ml or even more. That doesn't matter. Just how much solvent required, it is not the issue. Issue is that you need to dissolve 1 mole of substance in sufficient solvent. That means in that case, how much energy is changed? That is known as the heat of solution. So here we have mentioned when 1 mole of water is formed. Now we are mentioning 1 mole of substance or 1 mole of solid dissolved. That means the heat change during the formation of 1 mole of water or heat change during dissolve or go into solution for 1 mole of any substance. That is the heat of solution. Yeah, I mean. Okay, then the heat of solution, also referred to the enthalpy of solution or enthalpy of dissolution, is the enthalpy change associated with the dissolution of a solute in a solvent at constant pressure. Now, how we can calculate the heat of solution? This is very simple experiment. Maybe I'm not showing here, but that you can perform at your home. How? Just take a small amount of vinegar. All of you are familiar with vinegar? Okay. If you are familiar with vinegar, then do you know what is vinegar? As a chemist student from chemistry, acetic acid. Very good. Then what is the percentage for acetic acid in vinegar? No problem if you cannot remember, but if you can, that's very good. But there is nothing to be ashamed at all. So if you can remember, then fine. If you cannot, around 5.5% or 5 to 10% around. That is the acetic acid in the vinegar. Actually, CH3COOH. This is our vinegar. That means percentage, 5 to 10% acetic acid is known as vinegar. Okay. Now, if you can please take a container. then you can use the thermocol cup. That means insulated cup. We can take also plastic cup. That is also fine. Just if you have a cup made of thermocol or some polystyrene. Polystyrene cup, have you ever seen? No. Polystyrene cup, just previous slide I have shown. Okay, I cannot remove it. Just very simple. This is plastic, but I want to show normal cup made of polystyrene. So like this, or any plastic cup. Let us consider it as a plastic cup. This is made of insulated material. This is plastic also insulated material. So first take 100 milliliter of water. Let us take 100 milliliter of water. Now we may have vinegar. Let us better we take the vinegar, not water. 100 ml of so just 100 ml of vinegar, that means acetic acid. So first take a thermometer inside there. Read the temperature. Using thermometer is just you can read the temperature easily. Then add some sodium hydroxide. If we take vinegar and take sodium hydroxide, that will give you salt and water. That means we can get the heat of neutralization. Better we take only acetic acid and then we take water and sodium hydroxide. That can be the heat of solution. So what I have taken, that will be fine. So I don't want to have the reaction because here I am taking, if I take the acid plus NaOH, in that case we will have salt, sodium acetate, is it? And water. That means that will give a salt and water. But I want to make the solution, not any reaction. So just water and then I want to add sodium hydroxide, NaOH. Sodium hydroxide, you are familiar with the sodium hydroxide? You have seen the pill, sodium hydroxide pellet, tablet. In your laboratory, if you do any titration, I guess you will see the sodium hydroxide just like a normal tablet, like this shape. This is white crystal. So you can take any amount, maybe 2.5 gram of sodium hydroxide. We are taking 2.5 gram of sodium hydroxide. Just we can use any balance, but if you have the experiment you want to perform with sodium hydroxide, please never use your hand. Just with your naked hand, do not touch the sodium hydroxide. This is a strong alkali, so it can have the burning on the skin. So just we have taken 100 milliliter of water and then we read the temperature of the thermometer. Let us consider we have the temperature 20 degrees Celsius of the water. Now take 2.5 gram of sodium hydroxide. Then just you should have a lid over the cup. Add the 2.5 gram of sodium hydroxide into the water and little rotate. After rotation, what you will see, you can rotate or you can steer using the thermometer. In that case, you will see that the temperature of this thermometer is increasing. Why? Because when sodium hydroxide solid dissolves into water, it produces some heat. So that heat will increase the temperature of the water. So we can consider that the temperature, it was initial temperature, and we are getting the temperature around 26 degrees Celsius. That means we can see the temperature has raised 6 degrees. So that is our C2. That means delta T 6. Okay. Using 2.5 gram of sodium hydroxide. 2.5 gram sodium hydroxide increase the temperature of 100 milliliter of water to 6 degrees. It was 20 and finally 26. So the temperature delta T equals 6 degrees Celsius. So you are familiar with the word heat capacity of water. You know, the heat capacity of water equal to, that means how the temperature of water has been increased. Just the water absorbs the heat, how much heat has been released by the sodium hydroxide to the water, is it? So initial temperature was 20 and final was 26. So the how much heat has been released, we can write down Q equals MC delta theta. You are familiar with this equation? M is the mass of the water, or that means water plus sodium hydroxide. So we should have 100 plus 2.5. Is it? C is the heat capacity of water. 4.2 gram per Celsius. This, then delta theta is 6. From here we are getting multiplied with 6. Anything. Just if you subtract 20 to 26, 26 minus 20 into, if you want to convert into Kelvin, that will also give you same difference. So just we are getting 9 write down Kelvin. That means now you can get the value how much heat has been released by 2.5 gram of sodium hydroxide. So 2.5 gram of sodium hydroxide means how many moles? You can calculate, because we know sodium hydroxide 1 mole equal 40 gram. So 40 gram equivalents to 1 mole. That means 2.5 gram equals to divided by 2.5 divided by 40, that moles. So what is the heat of solution? We have found that from here, how much we have found, can you give me? And what is the number for this one? 102.5 multiplied by 4.2 multiplied by 6. The first one is 0.025. This one. Okay. 0.025, that much more. And here 102.5 multiplied by 4.2 multiplied by 6. 2583. 88. Yes, and 3. No. Not 8 and then 3. 183. Yes. 2583. That means then we should have, that is gram. This is gram. Ultimately, we should have some, which should be maybe calorie or joule, whatever. And just let us consider any unit. So 2583 calorie, or maybe I think we should graph it should be joule, whatever. Then from this mass mole, we are getting that energy. Then from 1 mole, how much you will get? Just multiply or whatever the divide we need to have. You are getting from 0.025 mole, 0.025 mole, you are getting 2583, 2583. Okay. So 2583 joule, whatever waiting. So for 1 mole, 0.0253. That is the number of it should. That means when 1 mole of sodium hydroxide is dissolved into water, we should get the value what we are getting. That is the heat of solution for sodium hydroxide. Divided by 2583 divided by 0.025. What is the number? Yes. 2.540. Okay. 0.0625. Okay. Then we should have this number here. 0.0625. 41,328. 328. That means that was joule, and then if you convert into kilojoule, yeah, should be for, because here it was more, is it? Yeah, it is more joule per mole. So that will be kilojoule per mole. That is the heat of solution of sodium hydroxide. We can estimate even better what I have mentioned, that the acetic acid, that is vinegar, that would give you the reaction sodium hydroxide, and but in your home you cannot have the sodium hydroxide available. You can get the vinegar, but you cannot have the sodium hydroxide. So the heat of solution is very simple. That means when you dissolve 1 mole of any substance in sufficient solvent, how much energy is changed. Normally, we should use the word change, not increase or release, because if you write down change, then you can easily understand either increase or decrease. Are you familiar with the bonding energy? No? Bonding energy. How you can calculate the bonding energy? For any molecule, you have the bond hydrogen, oxygen, hydrogen, like this. So, what is the definition of bond energy? The energy released when one bond is formed, or in another way you can say how much energy is required to break the bond. Is it? So now we will see, here you can see one information. Solute particles separate from each other. Let us consider we are dissolving sodium chloride into water. Then we have sodium chloride, one molecule, another sodium chloride. This is our two solute molecules. They have some interaction with them. So when these sodium chloride molecules are dissolved into water, in that case, they have to break this bond. That means within two different molecules, so it needs some energy or it releases some energy. That means when it needs to break the bond, you need to supply some energy. Is it? For any bond breaking, you need some energy. So solute particles separate from each other. This is one molecule, this is another molecule. So when they separate, we get delta H solute. Solvent particles separate from each other. Solvent particles, water. We have water. We will have hydrogen bond between two water. So just let us show like this here, whatever this. Just so these two molecules, that means the solvent molecules, we need to break this bond, and solvent particles separate from each other. That is the value delta H solvent. Now, when this solute and solvent mix up, that means they dissolve, they will form some bond in between this and this. So solute and solvent particles mix. When they mix up, they will form some bond and they will release some energy. Okay. So what is the heat of solution? Actually, what we have calculated in previous math. So heat of solution is the heat of solute. What we have mentioned that when this is solute, this is the heat of solvent plus this is the heat of mix or mixer. That means actually this should be in opposite sign, because when this molecule breaks, it needs some energy. When these two molecules break, then it needs some energy. When this bond is formed, it releases some energy. So ultimately, we should have like this way, some minus sign. But that is also, we can write down the, as already we have specifically mentioned that delta S is the energy for mixing. So we can write down even in terms of positive also. So what is the delta H of solution? It's just the summation of the heat of solute, heat of solvent plus heat of mix. So that is the heat of solution. Okay. Any question? Okay. For ionic solids in aqueous system, ions get surrounded by water molecules forming hydration shell. So heat of hydration equal delta H of hydration equal, heat of hydration equal delta H solvent plus delta H mix. So just if we have some ionic solid dissolved into water, in that case, like this one, in that case, what will happen? That the ions will surrounded by the water will be surrounded. For ionic solids in aqueous system, ions get surrounded by water molecules. That means all the ions what we have, maybe sodium plus, chloride minus, this will be surrounded by water molecules. These are water molecules. Maybe it is hard to see. This is oxygen, this is hydrogen, this is hydrogen. This is oxygen, this is hydrogen, hydrogen. So some white dot, it can be considered as hydrogen, and these are the ions. These are the ions, and here water molecule. This is another water, this is another water, water. So all the ions are surrounded by water molecules. So easily we can write down the delta H of hydration equal delta H of solvent. That means what we have the solvent water and the delta H of mix. Now we will learn about the colligative properties. Actually, that was the chapter what we have started, the colligative properties or collective properties. Collective properties, those properties of a solution that depend on the number of solute molecules, irrespective of their nature, with respect to the total number of molecules present in the solution are called colligative properties. That means if you have some solution, to make solution you need solute and solvent. Okay, so you have 200 ml of water. Now, all of you are familiar with the boiling point of water. How much? 100 degrees Celsius. Okay. So, 100 degrees Celsius. And melting point? 0 degrees Celsius. Is it? The melting of ice, or you can say freezing of water, that can be just melting of ice or freezing of water, that can be same thing. Just we write down. So just this is our liquid water, 200 ml. Now if you add some sodium chloride, maybe 2 gram sodium chloride to this, what do you think about the boiling temperature? I have mentioned that the boiling temperature is 100 degrees Celsius for pure water. Now, if we add 2 gram of sodium chloride into the water, then 200 ml water, do you have any idea that the boiling temperature can be changed, or it will remain same, or it can increase or it decrease? Yes. Just we are adding 2 gram of sodium chloride. In that case, what it can happen for the boiling temperature? I have changed the slide because there is the answer in that slide. Yes, you couldn't realize, but I know there is some the answer is there. Okay, that means you are considering, but we need to understand what will happen, because so first let us consider that this is our liquid 200 milliliter. Now we are adding some salt, that is non-volatile. That means water is volatile, is it? If you keep some water into a container for a couple of weeks, then after a couple of weeks you will get that some of the water has been gone away. Okay. That means the evaporation process happens. But if you put sodium chloride for a couple of weeks, you will see that nothing changes. So sodium chloride is non-volatile. So we are adding some non-volatile solute to the solvent. Now we can change that the characteristics of the solvent can change a little bit. So what characteristics we are considering that will be changed? Now see, we have 4 different types of characteristics. What? Vapor pressure lowering. That means if we add some solute, non-volatile solute to the solvent, in a pure solvent, in that case the vapor pressure of the solvent can be reduced. We will discuss why it reduces, definitely. Then boiling point elevation, that means enhance. it increases the boiling point. Already some of you have mentioned that it can be increased, but I guess none of you know why it can increase. Okay, we will learn today why it can increase the boiling point. Then freezing point depression. That means the freezing point, that means the ultimately we can say the melting point. Is it? Melting point can be decreased or depression. And then osmotic pressure. These four characteristics of the solution we will learn today. So first we will learn vapor pressure lowering. So how it reduces the vapor pressure. First, we are preparing the lowering of vapor pressure. How it lowers? You can see the slide here. This is our liquid, pure liquid. This is our liquid surface. That the line, black line. That is the liquid surface. Now, when there is nothing, only the pure liquid. Only the pure liquid is there. So, what happens in the surface? From the surface, many molecules can go out. That means by evaporation process. So, if the container is closed, in that case, we can get the vapor above the surface of the liquid. So, it is possible to get many molecules evaporated from the surface. But as you add some non-volatile solute, in that case, when you make the solution, what will happen? Previously, you had all the solvent molecules here and here. Let me write the solvent molecules. Now, when you are adding some non-volatile solute and you are mixing to get the solution, now you can guess some of the solvent molecule has been replaced by solute. So you can have one solute molecule here, maybe another here, some here, or some here, like this. So this molecule will not evaporate. Is it? So previously all the molecules from the surface could get evaporate. So many molecules can get into the gaseous state. But when we add some solute, non-volatile solute into the solvent, in that case, the number of particles, that means number of solute. If you add many solute molecules, what will happen? It will occupy many spaces. So, in that case, what will happen? The possibility of evaporation of the solvent molecule will increase or decrease. Any idea? Oh, sure. In general, when there is nothing, that means only the solvent, only water, we have the surface. So, liquids can escape due to evaporation process easily, because from here we have only surface, sorry, only the solvent. Now, in that case, we will have many gas molecules, because open surface, from the open surface, it can escape many water molecules into water vapor. But if we add some non-volatile solute like a sodium chloride or something else, in that case, the composition will be two here, is it? One is sodium chloride, another is water. So, if there is one water molecule, at least one water molecule in the surface, let us consider that. In that case, the possibility of evaporation will increase or decrease? Sure. Nothing to be confused. Just as the amount of water has been decreased, is it? By ratio. Previously, everything was only water. Now we are adding something that is not volatile. It will not evaporate because sodium chloride will not evaporate. Okay? In that case, what will happen? Just previously we had lot of here. I'm not going to draw this. So here we had lot of water molecules in the surface. So it's easy for evaporation. But if you have some sodium chloride, that will not evaporate at all. So if you have any molecule here in the surface, if there was not these molecules, then it could evaporate easily. But as we have some sodium chloride molecules, then the evaporation process will be hampered. It will reduce. Therefore, how many molecules of vapor will come here? That will be higher or lower than normal. So, the number of molecules evaporating is getting reduced. That is the vapor pressure. That is the result. That means if you add any solute molecules non-volatile, so easily in normal case the liquid can evaporate easily. But if you add any solute which is non-volatile, that will contribute in the composition and by fraction, whatever the amount, maybe we are adding 2 gram, 5 gram, 10 gram. As we increase the amount, what will happen? Previously we had maybe 4 molecules, when we add 2 gram. We have 4 molecules in the surface and rest of them over there. Now if we add 5 grams, then we can expect few more molecules. In that case, the possibility of escaping the molecule, that means the water molecule, even decreasing. Therefore, the vapor pressure for this region will decrease. That is the explanation how the vapor pressure of the solution decreases when we add any non-volatile solute to the solvent. That means the vapor pressure of pure solvent is higher. When we add some solute, that the vapor pressure decreases.
So boiling point also increases.
Yes, boiling point increases. Now, from here, you can get some idea. Can you guess? We have mentioned that boiling point elevation. That means the boiling point increases. Now you can guess, have you have any idea how the pressure cooker works? Okay. Sorry?
For temporary, it's like isolated system.
Isolated system, that's fine, but why do we use pressure cooker? You want to cook faster. Then how it works? We are using same thing. If you cook into a fry pan or pan, any pan, okay, yeah, some of you have the idea, but you cannot explain very well. Just in that case, that is not a big issue because still you are in learning. So you need to learn how to talk to people, how to convince people. That is the part of your training. So you need to learn first. any substance boils when the surrounding pressure equals the vapor pressure. If the vapor pressure of the substance equals the pressure of the surroundings, then that substance will boil. So when we use pressure cooker, we are, as she mentioned, that we are using isolated system. That means we do not allow the pressure to escape. That means the pressure of the, maybe I can draw the pressure cooker. Just simply, you have a lid, moving like this, and you put water here. That is our cover only. So you have rice or then potato, whatever it is. So you have water. To boil, you must need water. Is it? Now, water, rice, potato, whatever we have inside. Normally, when we cook in the pot or in any pan, then it boils when the water, when we heat up, normally the water boils at 100 degrees Celsius. That is very common. But if the container is closed, now you are heating and water vapor is increasing. Sorry, lot of water molecules are coming out. But as it is closed, the gas or vapor cannot escape. That means the pressure in this region increases quite a lot, and when this water will boil, the time when the pressure of this water, vapor pressure of water, become equal to the vapor pressure here. That means here we have already very high pressure. So if you want to boil the water, that means we have high pressure at the surrounding, and you have, if you want to boil the water, you need to have the pressure of that water need to be equal to the very high pressure. So if you want to have the high pressure, you need to raise the temperature more. So you can raise the temperature even higher. Normally we cook at 100 degrees Celsius, but if you can cook in pressure cooker, that can help you to increase the temperature up to 110 or 115 degrees Celsius, so that it takes shorter time to cook whatever we have inside. So just that is the gist, that when any substance boils, just lowering of vapor pressure, what is you have finished, vapor pressure solution, everything done. Okay. Okay, I will discuss this one later. Boiling point elevation. The boiling point elevation describes the phenomenon that the boiling point of a liquid will be higher when another compound is added. Just as we have mentioned that in water, if we add some non-volatile salt or non-volatile solute, in that case, that the boiling point will increase. Now, why increases? The will be higher when another compound is added, meaning that a solution has a higher boiling point than a pure solvent. That means, as we have mentioned in the previous discussion, that when we add the solute into the solvent, the vapor pressure reduces. So if the vapor pressure reduces in the pressure cooker, we increase the pressure so that it can boil in higher temperature. So if the boiling temperature, so if the pressure reduces, So it will boil at boiling point elevation. So now I'm going into maybe wrong way. Just let me see. This happens whenever a non-volatile solute such as salt is added to a pure solvent such as water. So here we can see that if we add, you can see this is the percent composition of solute. If you add very a small amount of, or initially you do not have any solute, you can see that the boiling point is around about 99. This is our 99 and little bit above, maybe we can consider this is 99.5. So maybe this is 99.1. Okay. When we are not adding any, that means 0% of solute, our boiling point is 99.1 degrees Celsius. Now, if you add a small amount, that means 10%, 10% of total, 10% of solution, that means if we take the solution 100 milliliter water and 10 gram of sodium chloride, in that case we can consider that is 10% around. It should not be exactly 10%. If we 10 out of 100, that can be 10%. So we are considering approximate 10%. So if we add around 10 gram of sodium chloride, then we can expect that the boiling point of that solution will go around 100 degrees Celsius. If we go for even higher percentage, previously we have mentioned that as we increase the percentage of solute, the vapor pressure lowers. Okay. Then we will discuss why it lowers. A liquid boils when external pressure equals the vapor pressure. Already mentioned. That means what happens for the pressure cooker? That means at higher pressure, we can boil at higher temperature. Okay, so a liquid boils when external pressure equals the vapor pressure. Vapor pressure of solvent is lower in solution than for pure solvent at any temperature. So if you have pure solvent, it will have the vapor pressure for minimum or maximum. For pure solvent, maximum. Yes, because already in the first discussion we have mentioned that the lowering of vapor pressure when pure solvent, in that case here we have seen that when there is less amount of or 0% solute, we have the maximum pressure, and if we have certain amount of solute, then the vapor pressure has been decreased. So as for the pure solvent, we will have the maximum vapor pressure. Then at boiling point, solvent does not boil. So as we increase the percentage, or as we add some solute to the solvent, that means mixing the solution, making the solution, the solvent does not boil. Higher temperature required to the external pressure. So as we have mentioned that when we add some solute, the pressure reduces, vapor pressure reduces, and then it is required higher temperature to get the higher vapor pressure. At that temperature, it will boil. So we can say that at boiling point, so that means at 100 degrees Celsius, if we want to have consider for water and sodium chloride, in that case, the water solution with sodium chloride will not boil at 100 degrees Celsius. It will boil little bit higher, maybe at 101 or 102 degrees Celsius, something like this. So I should go for the phase diagram. That is a very important thing. Phase diagram. Here you can see some curve. This is a diagram or representation of the physical state of any substance. Now, a phase diagram lets you work out exactly what phases are present at any given temperature and pressure. That means if you have a substance and you know the temperature and pressure, then you can easily understand what would be the phase. That means if it is solid, liquid, or gas, or any other state. So we can easily understand about the phase by knowing the temperature and pressure of that substance. So we can have the pattern, how it changes. This is the temperature and this is pressure. If you increase the temperature for any substance, let us consider for a liquid. This is our liquid, that is from here to here. This is our liquid region. So, these are boundary in between. This is triple point liquid, and it should be higher temperature, so it should be gaseous. Okay, so if you increase the temperature of liquid water, easily you can guess that it will convert into gas. But at the same time, if you change the pressure, in that case, you can modify where the liquid. This is a curve where above this curve, that is above this is high pressure, this is high pressure, and as we go from left to right, the temperature is increasing. This is our temperature axis. So first, this is a point, what is known as triple point. Triple point means a certain value of temperature and pressure where all three physical states can exist. That is triple point, and this is very important for water. In the next slide, maybe I have the value. What happened? This is not working. Okay. Triple point, the unique temperature and pressure at which the solid, liquid, and gas phase of the substance are all in equilibrium with each other. This is the temperature and pressure. This is our temperature scale, and this is pressure. So, at this point, if you go from here to here, below this, all are gas. Above this, liquid. If you go by on the left, then it is solid. So, solid means this is 0 degrees Celsius. If you go for beyond 0 degrees Celsius, this is our 0 degrees Celsius if you consider. So, this is 0 and this is 0.01. So, if you go beyond this, all water is ice. And if you go above this, it should be in the liquid form. But if the pressure is, this is 1 atmosphere. If the pressure is low, in that case, even at high temperature, at this temperature and very low pressure, you can have the water in liquid, solid form. This is gas. This is gas. So below this curve, here you can see below this curve, everything is vapor because at high temperature and very low pressure. Below this above the red curve, everything is solid. Everything is solid. This is high pressure and low temperature. So above this curve, this red curve, everything is solid, and in between this blue and green, this is liquid. So if you go beyond this or beyond this, you will get two different phases. So how we can represent the phase diagram lets you work out exactly what phases are present at any given temperature and pressure. So if you know any value of temperature and pressure, then easily you can understand what phase of that substance exists. Either this region, this region, this region, any fine. So phase boundary, that's another term. Just easily you can understand phase boundary. This is the line above this one phase, below this another phase. So we can consider this is a phase boundary. Even this one above this is solid and below this liquid. So that is called, this line is called as phase boundary. Even this one also, below this is gas, and above this is solid. So that is phase boundary, and this is the point what we call triple point, and triple point for water. This is the triple point of pure water is 0.01 degrees Celsius and 4.58 millimeter or 621.2 Pascal of mercury, and is used to calibrate thermometers. If you have, normally we use mercury in the thermometer, is it? So if you put this temperature, then you can consider that the temperature of that water is, so this is our standard. By comparing with this, we can calculate or we can standardize the thermometer to give the mark where it should be 100, where it should be 0. Just we use that standard and then we mark up the thermometers. So boiling point elevation, a liquid boils when external pressure equals the vapor pressure. Vapor pressure of solvent is lower in solution than for pure solvent, already mentioned. Freezing point depression. How we can consider that the freezing point can be reduced. Okay. Freezing point depression is the phenomena that describes why adding a solute to a solvent results in the lowering of freezing point. That means when we add some non-volatile solute to the solvent, that means when we are mixing or preparing some solution, in that case the freezing point of the solvent, freezing point of the solution, freezing point of the solution will decrease. But why? Because in the next slide, when a substance starts to freeze, just normally any substance, let us consider for ice. First, we had liquid water. Now, at liquid state, the molecules can move little bit freely compared to ice. So, when the molecules try to start to freeze, that means the molecules, the movement of the molecules or kinetic energy of the molecules decreases, so that the molecules come close together and they can have some proper orientation. That is, there is no solute, only pure solvent or pure molecule, anything. When a substance starts to freeze, the molecules slow down due to the decrease in temperature, and the intermolecular forces start to take over. That time, the intermolecular forces, that means kinetic energy reduces and the movement it decreases. So in that time increases the attraction force, intermolecular attraction force increases. Therefore, the molecules will then arrange themselves in a pattern, that is proper orientation, what we said, and thus turn into solid. That is common way. All of you are familiar with the process, how a liquid can be converted into solid. Now, if we add some non-volatile solute, what will happen? For example, as water is cooled to the freezing point, the molecules become slower and hydrogen bonds being to stick more eventually, creating a solid. That's what we already mentioned for the example. Just when we want to convert liquid into solid, that time the movement of the molecule decreases. That means, for example, if we say for water, the liquid water, when it starts to freeze, the hydrogen bond sticks. It becomes fixed, and that time the molecule try to become freeze, and we can get the ice. Now, if salt is added to the water, the Na plus and Cl minus, that is non-volatile salt, what we have mentioned, this Na plus and Cl minus ions attract to the water molecules and interfere with the formation of large network. Therefore, so for water molecules, when it freezes, it should have very large water molecule network. That means hydrogen bonding, strong hydrogen bonding. But when we add some salt, the ions, sodium ions and chloride ions, or any other ions, what we are putting inside the water, it will interfere the attraction between the molecules, water molecules, so that and interfere with the formation of the large network solid known as ice. Then it should have the attraction force little bit less. Is it? In order to achieve a solid, the solution must be cooled to a even lower temperature. So if it needs to cool even lower temperature, that means normally we should have the water molecules come close together and it should form a strong hydrogen bond. But if we add some salt, in that case, it's very hard to come close together because we have some extra ions which interfere the bonding attractions. Therefore, we need to cool more to come close to the water molecules to become freeze. Therefore, we can say that the freezing point can be even reduces or it decreases. We have another way, adding solute to a solvent. How we can explain that how the freezing point decreases. Adding solute to a solvent will essentially dilute the solvent molecules. That means if you add let us consider this is your solvent, water. Now, what is the fraction? 100% for the water molecule, or if you consider the concentration of water is, let us consider 1 mole. That means we have very high concentration for water. Now, if you add something else out of water, maybe NaCl water I mentioning, in that case, the percentage of water will be decreased because overall, how we can calculate the percentage out of 100? Is it previously we had 100 water molecules out of 100. Now we have, let us consider 10 NaCl. Then how the percentage of water molecule decreases? Then it should be out of 110, is it? Then the percentage of water. Previously we had only 100 molecules. At 100 molecules, we had 100 water molecules. Now we are adding 10 sodium chloride molecules. Now the total becomes 110. So what is the percentage of water in the solution? That is 100 divided by 110. That means within 110 we have 100. That means percentage of sodium chloride, it should be 10 out of 110. That's simple. That means now you will say 100 out of 100 or 100 out of 110. Which number is larger? Either this or this. This should be. That means for here, which means the solution. Is it? When we added sodium chloride. In that case, in case of solution, the density has been decreased for the solvent, and for solute increased, because initially it was 0 out of 100, and now 0 out of 10 out of 110, or even you can write down 0 out of 110. No problem, anything, whatever. So the percent of solute has been increased and percent of solvent has been decreased. Now, adding solute to the solvent will essentially dilute the solvent. That means the concentration has been decreased for the solvent. According to Raoult's law, this leads to a decrease in vapor pressure. Already we have mentioned in the first statement. That means when we add the solute, non-volatile solute to the solvent, then the vapor pressure decreases. Considering the fact that the vapor pressure of the solid and liquid forms must be the same at freezing point, because otherwise the system would not be at equilibrium. The lowering of the vapor pressure leads to the lowering of the temperature at which the vapor pressure of the liquid and frozen forms of the solution will be equal. Similarly, as we have mentioned for the elevation of boiling point, so just it should be at the same temperature as the pressure. If the pressure becomes equal to the surroundings, at that pressure it will freeze up. So as we can see that the vapor pressure decreases when we add the solute. In that case, it will take even more pressure, sorry, not pressure, it will need to reduce the temperature even lower to cool. So by this way we can also explain. And lastly, we have one thing, the osmotic pressure. Just the last topic for today. So the osmotic pressure, all of you are familiar with the diffusion. Okay. The diffusion means if you put some scent in somewhere, that means the something dispersing or distributing from the high concentrated area to the low concentrated area. So if we have some gas molecules like this, if you have the open space and these molecules can escape everywhere. It can get from high concentrated area to low concentrated area. That is called as diffusion. But if you have some semi-permeable membrane and you have two solutions of different concentrations, let us, this is one container and this is another container, and you have the semi-permeable membrane. All of you are familiar with the semi-permeable membrane? What can penetrate through the semi-permeable membrane? Solute or solvent? Solvent. Okay, that's very good. All of you are familiar. So let us consider this is our membrane and you have very, I should write down here, very high concentration. This portion has more number of solutes, and this portion has less number of solutes. That means the concentration of the solute is very low and concentration of solvent is very high. Okay, and it is separated by a semi-permeable membrane. Now, if these two parts are separated by a semi-permeable membrane, then the solvent will transfer from one to another. What would be the direction? Right to? Sorry? Okay, from high to low, that is the diffusion. But we are going to learn about osmotic pressure. So, in case of diffusion, you don't need to have any semi-permeable membrane. As we are separating with semi-permeable membrane, in that case, these solute particles will not be able to transfer. So, only the solvent molecules will be able to transfer through this membrane. In that case, where the more concentrated solvent, that means less number of solute particles. So, the solvent will transfer from this way. That means actually we consider this is the low concentrated area to high concentrated area. But if you say in case of solvent, you can consider the high concentrated solvent. Here we have relatively low concentrated solvent in that case, but normally we should consider that the concentration in terms of solute. So this portion has very low concentration and more solvent molecules. These more solvent molecules can transfer only the solvent molecules can transfer through this membrane. Therefore, this process is known as osmosis. Is it? Osmosis. Now, if you want to prevent the penetration of solvent, in that case, you need to apply certain pressure, which is exactly equal to the pressure how much the solvent is coming to this region. So, if you can apply that much pressure, in that case, no solvent will transfer in between. Therefore, that exact value of the pressure, what is required to stop the osmosis, that is known as the osmotic pressure. Understand? Any problem? So here you can see what is the figure. This is your pure solvent, this is solution. So this is our semi-permeable membrane. Here, whatever is showing here. The solvent molecule can transfer, not the solute molecules. So no solute molecules can transfer. Just semi-permeable membrane. That means the word comes from the only one component will be transmitted. Okay. So which component will be transmitted? Relatively a smaller size. That means particle size. Those who has the smaller particle size, that will be transmitted. So the solvent molecule has a smaller in size, therefore the solvent will transfer. So by this way we can understand the process osmosis and how much pressure is required to prevent the osmosis, that is known as osmotic pressure. So this is the end of today's class. If you have any question or comment, then you are welcome.